Okay, so I want to show you a computational way to calculate alpha diagrams. At this point in the class, you probably already use this, so I'm not going to show you how to download it, but if you need to, you can just go to Google and search for Hydra Medusa, and the first or second hit, either one, will provide you either a Windows or a Mac Linux download. So Hydra Medusa, these two pieces of software. Hydra is a collection or database of log K values, equilibrium values for a whole bunch of different reactions. And then Medusa is the plotting software that we actually input the data into and plot these complex diagrams. And this is how we do systematic treatment of equilibria using software. This is just a freeware version, but it's really useful. What's cool is not only can this do systematic treatment of, like metal ions in solution like we did for lead and lead phosphate, we can also do simple acids and bases, both strong but also weak. So I'm going to give you a quick tutorial on how to use this because it can be really helpful in checking your own work. I'm going to do it for H3PO4 first, which is a triprotic strong acid. And then I'll do it for EDTA, which is a hexaprotic weak acid that we're going to talk about quite a bit as a whole chapter dedicated to complexometric reactions between EDTA. And it gets complicated with equilibria there, and so this is a really nice tool to be able to fall back on. So when you're using this software, if you haven't used it already in the Flint tutorial, then the way that you are what you're looking for is a selection of a component, and then a component is the simplest representation of a particular equilibrium reaction. For instance, if I wanted to model the dissociation of water, I can't control both hydrogen ion and hydroxide ion concentration simultaneously because one is dependent on the other. I can only choose one component to model. It doesn't mean that I can't then see what the concentration of the other species is. That is exactly what we're trying to do. It just means for component, those are our inputs. What input do we want to control? In some cases, you want to control the hydroxide concentration. In other cases, you want to control the hydrogen ion concentration. This software is meant for aqueous systems, so it's always going to start out and open the software with H plus as the default component selected. So we're just going to leave it there. And I want to do H3PO4 phosphoric acid, so I'm going to go up to phosphorus, click that on the table, and you'll see a whole bunch of different components that are available for P. Remember, a component is the simplest representation of a particular equilibrium, and so you can see PO43 minus there, but you don't see all of the other species within the phosphoric acid system. What they're going to show you are all just the simplest representations of those systems with no protons attached. So the second one is is phosphite, HPO3 2 minus, and so you see all of these different systems. These are all separate equilibria where they don't depend on each other necessarily. And so I'm going to select PO43 minus, and when I select that component, then what comes with it are all of the complexes that are associated with PO43 minus, which are the protonated versions of that. This is all we need to start with. So then I'm going to go to File, Save and Exit. And then I'm going to save and click that first save button. And what I can do, I'm going to save this as H3PO4 alpha diagram. I already did this, so I'm just going to grab that file so I don't have to type it out. Click yes, sure, I'll overwrite it. And then it's going to prompt me, it's going to open up the Medusa software. So it's taking that data file that we just generated. So when we selected those, it didn't look like much, but it actually is now carrying over a whole bunch of equilibrium data associated with all those complexes. So now I just need to go to Run, make a diagram, and the type of diagram that I want is a fraction diagram, and I want the fraction of PO43 minus on the y-axis, and I want to see that as a function of pH. And I'll just do this over the full range, 0 to 14. Click OK, and I can choose the concentration of phosphate, but for an alpha diagram it doesn't matter because the fractions are not dictated at all by concentration. They're only dictated by the pKa's, the relative pKa's. So this is all I need to do, and then I can go up to the top left, click Make a Diagram, and what I'll see is a nice alpha diagram for the phosphoric acid system as a function of pH. So this is super nice, super powerful. I highly recommend playing around with the software. The utility here is that you can change variables really quickly and see the outcome without having to calculate it yourself. And so for me, this helps in developing intuition even faster. So I use the software a lot, not just to check my own thinking, but also just to see what happens when I change this. So Hydra and Medusa can also model weak acids, although there's not a ton of them that are built into the database, though you can add those. And if you're interested in adding those, I can try to remember how to do that. It's pretty straightforward if you play around with it. You can add data to the database. You just need to know what the pKa or pKa's of that acid are. So here I want to do EDTA, but really any weak acid, they're going to be carbon-based. So I have my H plus already selected. Now I look at carbon and I can see all the different carbon-based species. All of these are weak acids. So I've got the carbonate. You know, if you can hover over it, it'll tell you what the species is. I have cyanide as part of HCN. I have thiocyanide as part of SCN, HSCN. I have cyanate. I have formate as part of formic acid. This is acetic acid, oxalic acid, citric. NTA is nitrilotriacetate. EDTA is what we're going to use, so I'm going to click that. I have glycine, the amino acid, and I have acetylsalicylate, and then hemoglobin is the HB, which is pretty fun if you're a biochemist. You can model any biomolecule in here as long as you have the relevant K data and you upload it. Okay, so all I need are the H plus and the EDTA for me to model the alpha diagram for that. So I'm going to do the same thing, file, save and exit. I'm going to save that file and open it as a Medusa diagram. I'm going to do EDTA alpha diagram. Click save, sure I'll override that, run, make a diagram, and now same thing, I want the fraction on the y and I want that for EDTA and I want to do that as a function of pH. I'm going to do that over the same full range, 0 to 14. Click OK, and then I want pH varied. Everything else is good. I should note, if you didn't already notice this or play around with this, the ionic strength, it can be varied here. The ionic strength, if you change this, if you know mu, that's where activities get incorporated. If you don't use that, activities don't get computed, and you're just computing for concentrations because the activity coefficient gamma is assumed to be 1. Okay, so I can make the diagram, and what I get is this really nice diagram. So EDTA is a hexaprotic acid. There are 4 carboxylic acids and then 2 ammonium groups. And so this is a really nice representation. What we'll see and what we'll use this for is to look at how the speciation then interacts with metal ions in solution. So this is super awesome because now not only could we have computed this, we could have computed this in the presence of another metal ion and then controlled that metal ion concentration. So remember this when we get to the EDTA, the complexometric chapter in a few days.